Hello fellow engineering students. Do you know this man? Or maybe this man? Chances are, you'll have to take a few of their classes later on. But we're Group 8, and we're here to help you out. You see, in 1845, a man named Gustav Kirchhoff introduced fundamental electrical laws to the world. One of his laws was his voltage law, which states that the sum of the voltage drops around a loop has to be equivalent to 0.
In performing our experiment, this is the equipment that we used. First, we used a multimeter in order to measure voltage drop. For power supplies, we use an Arduino Nano and a 9-volt battery for varying voltage sources. We do all of our circuit construction on a breadboard. In our circuits, we use resistors, which we are able to change which one we're using in order to affect the voltage. And then we also use LEDs as constant voltage drops. Here you can see the experiments we ran. The first one we did was to simply test with varying voltage with one power supply and one resistor. Our prediction was that we would see the voltage drop across the resistor increase as the voltage of the power supply increased. And indeed, that's what we saw. The tester we're using is called a multimeter. It requires us to plug in 2 test leads, one before the component in the loop and one after the component, and it tells us what voltage we see. Something important to notice as we're taking the measurements is that we skip measuring across the wires themselves that are connecting the components. This is because the multimeter we're using isn't sensitive enough to detect the minute voltage drop across the wires themselves, so we omit that part for brevity. This is our second test, with the power source and 2 resistors in series. In it, we increase the voltage change across one resistor by varying its resistance. Our prediction was that, as we did, the voltage change in the other resistor would decrease in magnitude, so that they always have the same total voltage drop. Once again, that's what we see. This is our final test, with the power source and 2 resistors wired in parallel. For this experiment, we predicted that the voltage drop across both resistors would be equal in magnitude to the voltage across the power source. We do not expect them to have a constant sum like the previous one, for reasons that will be explained later. However, keep in mind that, the way we're measuring it, the power source is positive and both resistors are negative. This test again verified the law, but it may not be immediately clear why, since viewers who are paying attention will notice there's a loop that includes 2 resistors that doesn't sum to 0. So, to explain this and the previous circuits, here's Miranda.
This is a simple series circuit. When you start at a point, you go until you reach the battery, and that is called VB, and then you continue to go until you reach R1, which is VR1, until you come back to the point. Our law states that VB plus VR is equal to 0, which means VR equals negative VB, which is a linear relationship. This is a 2 resistor series circuit. Following the same processes as we did in the simple series circuit, we find that VB plus VR1 plus VR2 is equal to 0. R2 is the dependent variable and R1 is the independent variable, while VB is a constant as shown here in this linear relationship. This is a parallel circuit. We have 3 loops. This is loop 1, this is loop 2, and this is loop 3. These 2 are very supported by our data. However, this one appears to not be supported by our data, but because we measure one of the resistors opposite, it is supported by our data.
Oh, didn't see you there, just working on my circuits project. So I bet you're wondering, why did we just teach you about Kirchhoff's voltage law? And it's not just because we had to for this class, but because it's applicable to everything we use day to day. Your cell phone, your computer, things that you wouldn't even think of. So in doing our experiment, there's a couple of things that we have to take into account. The error of the multimeter. Wires have a little bit of resistance in them. The power supplies vary while we're doing the experiment. Resistors aren't exact values. This law is entirely fundamental to everything electronic. Without the law, we wouldn't have the framework to dream about things such as computers or light bulbs. Ultimately, without Gustav Kirchhoff, the world would be left in the dark.